last time, and we covered what we mean by traffic flow theory. Okay, so basically we are trying to understand how traffic moves. Okay, it can help us with these things. Okay, and you can also calculate things which are not related to traffic, such as crashes, travel time, air pollution, and so on. Okay, then we looked at some factors. There are three main factors. We have flow, we have density, and we have speed. Okay, we have looked at all three factors. Okay, this is the equation to convert the flow into rate of flow. Okay, so flow is basically per unit time, and then you convert it to per hour. Then you have density and speed. Okay, and the speed should be mean speed. Okay, it can be time mean speed, space mean speed. Okay, so the first one is simple mean, arithmetic mean, and the second one is the harmonic mean of the speeds. We looked at this equation, then we looked at the concept of time headway and space headway, the interval between two vehicles. Okay, the distance between them is space headway, the time between them is time headway. Okay, then we looked at this figure, which is called the time space diagram. You can get speed, you can get stop delay, and you can get the headwind spacing from this diagram. Okay, I believe we didn't cover this example, so this is related to the things which we already covered. So you see there are three vehicles on the road, right? Okay, and you know the distance between the start to the end of the cycle, okay, which is 300 feet. Now for each vehicle, the distance is given, the length of the vehicle is 20 feet. Okay, all vehicles are 20 feet long, which is basically cars. Okay, the velocities of the vehicles are measured, you can see it over there. Okay, for each vehicle we know the velocity, the speed. We have to calculate the flow, the density, time mean speed, and space mean speed. Okay, you are already given four values of speed here, right? Okay, and you have to calculate these 1, 2, 3, 4. 4 things. Out of these 4 things, I can calculate which one I can calculate immediately. We are given 4 speeds. Time mean speed, okay, which is basically the mean speed. Okay, so what is the mean of these 4 values? Four zero. Okay, so time mean speed, the simple mean of that. Right? If I need the space mean speed, I do the harmonic mean. Okay. Again, the 4 speeds, but not the simple mean. This one. Okay. So what are the 4 values? Forty-five. Again. 40. 30. Okay. So then what would be the space mean speed here? Yes, any questions? something which I mentioned last time as well. They are not same. They are for the same cars, but not same. Okay, and which one is supposed to be lower? Spacing. Okay, always. And here you can see the difference is like more than 1 mile per hour in the mean, which is quite a lot. Okay, now I have to calculate flow and density as well, right? Okay, so flow is basically number of vehicles per unit time. Okay, number of vehicles per unit time. So to calculate the flow, I have 4 vehicles here, or I can calculate flow using okay, this is the equation for flow, right? Where n is the number of vehicles you observe. Okay. Now how many vehicles we have? 4 vehicles. Okay, so n is 4. Okay. Now in the question, did they say for how much time the vehicles have gone? Did they mention any time in the question? No, because they said if you read the question, they say it's instant of time. Okay, like a picture. Okay, so just took a picture of a photograph. There is no time here. Time is 0. Okay, I do not have the time, but I can use this to calculate or to give a general equation for flow, which is in terms of time, because I don't have time. So 4 clear? Okay. So to calculate the flow, just to clear your concept, to calculate the flow, I must know in how much time these 4 vehicles will pass. Well, if I know the time, I can put it as t, I will know the flow. What are the units here? Vehicles per what time? How much time? Hour. Because you are doing this, right? This is an hour. Clear? Clear? So you have to put the time here, but then you should know how much time these 4 vehicles will pass. Okay? Okay. Then we have density. Okay. So for density, density is vehicles per unit length. Vehicles per unit length converted into miles, because you cannot put them in feet. It will be very small, a fraction. Okay. So do we have number of vehicles? Do we have length? Okay. Yeah. We have 4 vehicles and we have 8 and 10. Okay. So how much do we get here? And then you have to convert it to miles. So 1 mile is 5280 feet. Okay, so 4 divided by this, then into miles. 4 divided by 300 into miles. How much? You are registered in 433, right? You are registered in 433 and you are in 432. Yeah, anyone? How much?
What was the question from the scale?
Vehicle per unit length.
So what will you mean hours per second?
Length is 300 feet.
So every
300 feet. Right?
okay.
And if you just take it from here to here, then what we want? Just take it from here to here. So 55 and 15, how much? 70. So if you do 4 upon 230, and then into what? How much you get? 4 upon 230? No, sorry, not 230. 210. 4 upon 210. Then into miles. 10. Okay. Okay, any questions? Okay, these are the equations. Okay, I'll explain them here. So even if you didn't take traffic, you will know the equation. You will know how to use it. Okay, and when you will take traffic, you will know how to take traffic. Okay, clear enough? But there is no like big science here. I will tell you. Okay, the first equation which you see is called the basic equation of traffic flow. This is the core, the root of traffic flow theory. Okay, which is flow equals k into mean speed. Okay, now we are saying mean speed is us. Okay, so which mean speed is us? We have two mean speeds, right? Which mean speed is us? Space speed. Okay, and yes, d dash is the mean spacing. The mean spacing, the distance between vehicles, right? So you will take multiple distance, you will do the mean, simple mean, d dash. Okay, so d is the spacing between two vehicles, and d dash is mean of multiple vehicles. What? Okay. get d dash here from here. D dash came from here. Okay. So K is density. So mean spacing is inverse of K. Mean spacing is inverse of density. Okay. Now we calculate density in the last question, right? What was density? Vehicles per length, right? Vehicles per length. Okay. So its spacing is inverse of it, which is length between two vehicles, right? So this is vehicles per length, and this is length between two vehicles. They are inverse. Got it? Okay? Okay. So if you take K from here and replace it with the inverse of this, you will get this equation. Okay. Let me do it over here. So my actual equation was Q equals K into this, right? And I am replacing this with 1 over d dash. Okay, so there will be 1 over d dash here. Okay, so it will be Q is 1 over d dash. Okay, and d dash goes here, US equals to this. Okay, clear? Clear? Okay. Then we have T dash here. T dash is the mean of headway in the two vehicles. Time headway. Okay. So T, small t is headway between two vehicles. T dash is mean headway of vehicles. Okay. Now mean headway of vehicles is inverse of flow. Mean headway of vehicles is inverse of flow. Now what was flow? Tell me. Vehicles per hour, right? Or vehicles per time. And headway is time. Okay. So flow is vehicles per time, and headway is time between vehicles. So they are inverse. Correct? Yeah. So now I will do what? This is my basic equation, right? And I said flow is inverse of headway. So now I replace flow with inverse of headway. So Q will become inverse of headway. Clear? Okay. So and I know no. What did we do? Yeah. And I know K is inverse of spacing, right? K is inverse of spacing. Okay. So K is replaced with this, and Q is replaced with this. Okay. So this is how you got this equation. I think I did a mistake. What is P dash? Headway is H dash. Sorry. Headway is H dash, not T dash. So this is average headway. Okay. This is the equation I'm talking about. Okay. So not T dash, H dash. So this is average headway. What else? So this is how we got this equation. We went there. Okay. Q replaced with inverse of headway. Okay. And K replaced with inverse of where is it? Inverse of space. Okay. So this is how we got this equation. So D dash is average spacing. US is space mean speed, and H dash is average of headway, time headway. Clear? So it is coming from here. And this equation Q is replaced with inverse of headway, and K is replaced with inverse of spacing. Clear? Okay. Now we come to what? T dash, which is the sorry. So T dash, I was saying T dash is average headway. T dash is not average headway. T dash is average travel time. Okay, so average headway is different. Average travel time is different. Headway is between two vehicles. Travel time is for one vehicle. Every vehicle has a travel time. Every vehicle has a travel time. Okay. So. So T dash is the average travel time. So you can, average travel time is the inverse of, what is this? Spaces. Right? Okay? So all these three things have an inverse. Okay? Inverse of flow is headway. Inverse of density is spacing. Inverse of speed is travel time. Make sense, right? Inverse of speed is travel time. But average values. Average values. You cannot replace them with single values. So the dash, you see, they are dashes, right? All of them have dashes. These are dashes representing what? They have. Dash means what? So what is the difference between H and H dash? The mean, okay? H is a single value. So if you see H in the equation, that's wrong. Okay? They become inverse when you take B. Alright? Clear? Any questions? Any problems? Okay. So if traffic flow is given 1800 vehicles per hour, we have to calculate average time headway on the segment. Flow is given, time headway is required. What is the relationship between flow and headway? They are inverse. Okay? We just do the inverse. Clear? Now, when you will do the inverse, flow is in vehicles per, what is H? Hour, right? Should the headway be in hours? Between two vehicles. Should we have hours? No, right? That should be in what? Seconds. So you have to do the inverse. You do the inverse and then do the inverse. How much do you have? They should do the simple inverse and then you do the conversion. 2 seconds. Which was H dash, okay? I cannot put a dash here, but you get it. Or I will write it dash. So you do the inverse of this, and then the conversion. Yes. Two seconds. This is for a very high flow value. This is, by the way, 1800 is considered as the capacity of highways and normal highways. So 2 seconds highway is very small. And this happens when highway has capacity. Clear? Any questions? Okay. These pictures show you the relationship between the three traffic parameters. The three parameters of traffic flow. What are the three parameters? Okay. These two and the flow. There? Three parameters. figures, you see two of them at a time. Okay. If you look at the bottom left corner, the one at the bottom, the straight line. Okay. You're looking somewhere else. Sure. Bottom left. See, now she's doing this. So, when I'm trying to make my calculus pretty simple, and this is what it is. Until I won't ask you in a month. I have to ask her, where is it? And she's okay. So bottom left corner, okay? The one between speed and density. Okay. Which is very simple. The density increases, what happens to speed? Okay. Density increases, speed decreases. Make sense? Okay. More density means what? More cars, right? If there are more cars, your speed will be less. But at least it should be. That's why they are putting more cameras. You are not listening to them, you are not listening to me as well. Okay, so density increases means more cars on the road, speed decreases. Okay, so that's the straight line. Okay, then moving on to the one which is bottom right. Okay, that's the one between flow and speed. Flow and speed. Okay, so before we move on to that, let me explain this one. There are two things written here. One is written as UF, the other one is written as KJ. U means speed, K means density. Okay, what is the meaning of F and J? Now you can see UF is the highest speed, right? This is the highest speed. Okay, after that the speed only goes down. So this highest speed is known as free flow speed. So UF is free flow speed. Clear? Okay, then we have KJ, okay, which is called as jam density. Again, the highest for the density. Okay, so the higher speed is called free flow speed, the higher density is called jam density. So at UF, what is the value of density? 0, right? So when speed is free flow, density is 0. No cars, right? That's why the speed is highest. And what is the speed and jam density? Yes. You were very worried to post the what would I do? Yes, not that. 0, right? Okay, good. So when you have jam density, you understand jam, right? Traffic jam. Okay, not the jam which you put on bread. This jam. Okay. So when there is traffic jam, there is no speed. It is 0. Right? Okay. Now we move on to the next figure, which is on the right hand side, at the bottom. Between flow and speed. Okay. I start from here. So what was UF? Free flow speed, right? So maximum speed is still the same, right? Maximum speed. Flow increases. Flow increases means more cars, right? More cars. Okay. So when there are more cars, the speed decrease. Okay. But it's not a linear now. It's not linear now. Here it was linear, right? Okay. But here it's not linear. It's curved. Okay. But what is the trend? It is decreasing, right? More cars on the road, speed decreases. Okay. But the flow is increasing, you can see. Flow is increasing, the speed is decreasing. Okay. Till you reach this point, which is called as Q max. Okay. Q max is maximum value of maximum value of flow. Okay. So when you reach, so what is Qmax? Maximum value of flow is called capacity. Okay. Qmax, maximum value of flow, is called capacity. Every height has capacity, right? I told you normally in balance we take 1800 liters per hour, right? Okay. So what happens after capacity? You reach capacity, high rate you reach capacity, but the cars are still increasing. What will happen? After capacity, what happens? Traffic jam, right? So in traffic jam, the flow increases or decreases? I'm talking about the flow, okay? Not the cars. Flow. The flow increases or decreases? Decrease, right? Flow will decrease. You can see the flow decreasing, right? Okay. And what happens to speed in traffic jam? Increase or decrease? Decrease. Okay. So speed keeps on decreasing, right? Speed is decreasing, speed is still decreasing. Okay. But up till here the flow can increase because you have not reached capacity. After this, the flow is also decreasing. So there are the two parts to this figure. One is before capacity, they call it uncongested flow. One is after capacity, which is congested flow. Okay? Uncongested, congested. Before capacity, uncongested. After capacity, congested. Clear? Okay? Any questions? Okay. Then we are only left with the last figure on the top, which is between flow and density. Yes. So here we are starting from 0. Flow is 0, density is 0, nothing on the road. Okay. More cars come, flow increases, density also increases. Both of them are number of vehicles, right? Number of vehicles per time, number of vehicles per mile, right? So number of vehicles increase, both of them will increase, right? Okay. So you see the increase now. Is it linear? No. Okay. But both of them are increasing, right? Density increases, flow also increases. Then you reach the point of Qmax. What was Qmax? Capacity. Okay. After capacity, can the flow increase more? Can the flow increase after capacity? No. The flow starts to decrease, right? But what about density? Still increasing. Okay. Density is still increasing. So what is happening? Here the density was increasing because the flow is increasing. Here density is increasing but the flow is decreasing. So where are these extra vehicles going? More density means what? More vehicles, right? Vehicles per mile, right? And flow is also vehicles per time. Both of them are vehicles. So one type of vehicle is decreasing, the other type is increasing. So the type which is increasing here, the number of vehicles which are increasing in density, they are not increasing in flow. So what is happening to them? Aliens are taking them? No? They are stuck in the jam. Yes. So they are coming. So they are increasing in density. But they are not moving. Flow is what? Flow is movement, right? Water flows, right? Means what? Water is moving, right? If I give you water in a bottle, will you call it water flow? You will call it? She is doing this. No, right? Water in a bottle is not water, it's not flowing, right? It's not flow. So when cars are getting stuck on traffic, there are more cars, but they are not more flow. Got it? Okay, so this is what is happening in this part. Okay, so after capacity, only density increases, but these vehicles are stop moving. That's why the flow is decreasing. Got it? Okay? portions here, one before capacity, one after capacity, right? What did we call them? Before capacity? No. What did we call them? Before capacity we call them uncontested. After capacity we call them contested. Same thing. Before capacity, uncontested. After capacity, contested. Clear? Okay. Okay, what else they are showing here? Yeah. So if you take the slope on this curve, slope. Okay. Slope will be what? Flow upon density, right? Flow upon density. If you look here, flow equals density into speed. So if you do flow upon density, you will get. Okay. If I take the slope, it will give me speed. Clear? Okay. Okay. To define traffic flow, there are two approaches. One is called as macroscopic, the other one is called as microscopic. Okay, so there are two approaches to define traffic flow or to model traffic flow. So there are two approaches to traffic flow theory. One is called as macroscopic, the other one is called as microscopic. Okay, so what's the difference between macro and micro? What is the difference between macro and micro? The words, I'm not talking about traffic. If I say this thing is macro, this thing is micro. Which one is smaller? Micro is smaller, right? Okay. So, when we say microscopic approach, I'm looking at small units of traffic. When I say macroscopic approach, I'm looking at big unit of traffic. Alright? The small unit of traffic is a car. Traffic is made of cars. Small unit of traffic is car. Big unit of traffic is flow. Got it? Okay. So when you are looking at the whole flow, you got this is a macroscopic approach. When you are looking at cars, individual, that is microscopic. Okay. Then both of them have their own models, but you should know the difference between them. We will discuss macroscopic in the coming. What we have discussed until now was macroscopic, the first one. And what we discuss after this is also the first one. Okay, so we are focusing on the first one. Okay, but there are some famous models in the second approach. Okay, the most famous, most common of them is called the car following theory or follow the leader theory. Okay, so in microscopic approaches, you will not cover that. That is given the name. You have an idea. Car following theory and follow the leader theory. In microscopic approach, they are saying traffic flow can be modeled on the basis of how one car is following the other car following. Okay, in both of these cases, you see the same word, right? We are seeing the same thing. So according to this approach, they look at traffic on how one driver is following the other driver. So microscopic approach is depending upon each driver and how they follow the other driver. Okay? So they are looking at each driver. Okay? Okay. So that's why they are more complicated. Thousands of drivers, right? In the last example we did, the flow was 1,800. 1,800 means 1,800 drivers. And I was looking at each one of them separately. That is microscope. Clear? Okay. Microscopic is easy. Okay. But microscopic has its importance and strength. So, like I said, we will not cover the microscopic theories in detail. Just give you the names and an idea. But macroscopic, now we will cover them in detail. Okay. We already know one basic equation of macroscopic traffic flow theory, which is which one? Okay, this is the basic equation of macroscopic traffic flow theory. Okay, and then there are others as well which are different. Okay, this is what we see, what we call as Greenshields model. Greenshields model. Okay, in this equation there are 4 parameters. You will tell me what are they. What is US? Space mean speed. What is UF? Free flow speed. Very good. What is KJ? Jam density. What is K? Density. Any density? Clear? Okay. So the equation is between 2 parameters. This equation is between 2 parameters. They are only using 2 parameters. Which 2 parameters? Speed and density. You said something like that, right? Yes. Okay, the answer equation is between speed and density. Okay. And basically, okay. Now we can use this equation and this one to calculate other parameters equations as well. Okay. So, for example, US. I can replace US from this equation. So US equals to what? Q upon K, right? US equals to Q upon K. So if I go there, so Q upon K equals US okay, and Q equals to what? Then Q equals to what? No. Now I want to drive this equation for Q. So Q equals to what? Yes, if I keep Q on one side, K goes on the other side, right? So what will the right hand side become? I have UF, then K, right? No. I only want Q here, so K will go on the other side, right? It will go on the other side, it will multiply, right? Okay, because you already have a K here. Clear or not? Any problem? Okay. So if you look at this equation is again between 2 parameters. Which 2 parameters? No, the new one. Flow and density, right? Flow and density. Do we have UF here? We still have UF, right? We still have UF. What was UF? Free flow speed. So why are we saying it is between flow and density, not flow, speed and density? Why? It is correct. The equation is between flow and density, Q and K. But what do you know about UF?
From the slope. From the slope.
No. UF is something constant. Free flow speed of the line. Okay, free flow speed was the maximum speed, right? Free flow speed was the maximum speed. It doesn't change. I can replace UF with a number, no problem. Okay? When we say the equation is between x and y, that means x and y are changing. Okay? If there is a constant in the equation, you not consider the equation for the constant. Got it? Clear? Okay. Then I can do the same thing. So this was the equation, I replace US, right? With the basic equation, right? Now I can replace K as well. So I keep this equation. In this equation I place k. So if I come back here, k equals to what? Q upon us. Okay. Then I place k with q upon us. So us is already there. I have uf upon kj, and now I will place this with q upon k. Okay. So what I want to do is have the equation between q and this is already between q and k, right? So I need the equation between q and us now. Okay. So I need q on one side and us on the other side. Okay. So I'll put it there and put it here. Okay. So us equals to uf on kj. This goes here, and then this comes on the other side. Okay, I just switch that.
Okay. The Q over the US.
Sorry,
The bracket.
which one?
The bracket is Q over US.
Q over U. Sorry. Yes. Q over U. Yes. The word is coming from here, right? Q over U. Okay. So I will keep Q over here and everything on the other side. Okay. So UF and goes here to cancel, right? Okay. So what will I get? Q equals US over kj minus US square. So let me just repeat one step more. So 2 times UF into US into 0 Okay, so Q on one side, all these things on the other side. Okay, so this will cancel out. Here it will become the square. Okay, so what's the final equation now? Q equals what? Tell me. US kj minus US square kj over UF. Clear? Okay. Any problem? Any question? Okay. Now if I go back, now you see this model here, right? Is there any square here? No. So it's a linear model, right? It's a linear equation. Between what? Speed and density. Speed and density. This one. Speed and density. So that linear equation, Greenshield model, is for this one. Got it? Okay. Now you see the other two are curves, right? They are not linear. So they must be square, right? So that's why we have the other two equations with a square. Okay. So these two equations are for these two curves. Clear? So the linear one is for the linear line, and the curve, the second degree equation are for the curves. Clear? Okay. Now, in both these curves we have something called as Qmax, right? Qmax was what? Capacity. Okay. Now when you reach capacity, the maximum point on the curve, and you reach maximum point on the curve, what happens to slope of the curve? Zero. Becomes zero, right? Slope becomes zero. Okay. So I already have the equations for these curves, right? The second degree equation. Okay. So if I want the slope, I have the equation for the curve. If I want the slope, what will I do with the equation? I'll take if you have the equation, you want the slope. What do you do? No. You take the derivative. Yes, you take 2 points if you are on the curve. I'm talking about the equation. The derivative of the equation is the slope. Got it? There. Derivative is the what? Slope. Okay. Can you give me the derivative of these equations? First of all, this one. So dq over dk. What will it become? If you take the derivative of this thing with respect to k, what will it become? This will become what? UF, right? And what will this become? This is now square, right? If you take the derivative, it will become 2 into this, right? The whole thing, right? So 2 okay, and we said what? When the slope reaches 0, slope becomes, curve reaches maximum, the slope becomes what? 0. So this is a slope, right? So this becomes 0. So if this is 0, then what is k? If this whole thing is 0, then what is k? Let me write it here. So UF minus 2 into UF upon Kj into K becomes 0. Okay, so K equals to what? Kj. Really? Kj only? What will happen to this 2? The 2 here. My other things are cancelling, yes. But what is happening to the 2 will not cancel, right? So K equals what? Kj over 2. Okay. Now this happens when slope is 0, right? Slope 0 means curve is maximum. Maximum was what? Qmax, right? Qmax is capacity. So K equals Kj upon 2 when it's capacity. Okay? And because it's a specific condition, so I'll not call it K. I'll call it K naught. Got it? Okay? Because it's a specific condition. K does not become Kj upon 2 in all the conditions. Only becomes when slope is 0. Slope is 0 when you have capacity. Okay? So K naught as density at capacity, which is Kj upon 2. Then, okay? Now, I'll do the same thing with this equation, right? This one also becomes 0. Slope becomes 0, right? Okay, I will take the derivative and so on. I will take the derivative dq upon what? D. What is the other parameter here? S, right? US. Okay. So here I will take the derivative with respect to US. There is no k here, right? I will take the derivative with respect to US. Okay. So same thing will happen. Okay. So if I do this, then dq or dus is this will become us minus 2 into kj on uf. Okay, and this becomes equal to what? 0, right? So us is what? Now? No. K. I don't say minutes. K is this. This is K. So now what will it become? US becomes what? K will cancel, right? Okay. So US becomes what? UF will go on the other side. So UF. And will it happen always? Is the slope 0 always? No. The slope is 0 when? Capacitor. Okay, so this is again at capacitor. So I will not call it US, any US, I will call it US naught. Okay, which is a speed when you reach capacity. Okay, there, any problems, any questions? Okay, so this is what they were asking us to. Okay, so what is U naught? It is speed when it reaches capacity. How much is it? Okay, I'll put naught here. Okay, and this one is K naught. Clear? Okay, moving on. So another model which is applied to macroscopic. We are still talking about macroscope. Okay, the flow, which is called the Greenberg model. So on my macroscopic there are two models. The other one, the previous one, Greenshield. So all the equations were for Greenshield. And we have this one which is for Greenberg. Okay, and you can see the Greenberg is more problematic because it's not linear. Okay, there's a log here, natural log. Okay, it's not a single model. Okay, so the first equation of Greenberg model is speed equals to this whole thing. Okay, where we already know kj and k, right? We know that. C is a constant. C is a constant. We don't know its value yet. But it's a constant, it's a number. Clear? So according to Greenberg, the speed follows this equation, which is depending upon density and it has a constant as well. Got it? Clear? Now let us find out the value of the constant. So what we do? We multiply both sides with k. Okay, so when you multiply both sides with k, okay, then what do? You take the derivative. So we multiply both sides with k, then you took the derivative. Okay, when you take the derivative of something which has a log in it, this is what happens. Okay, this is the derivative of the natural log. The number, the constant remains as it is, the log remains as it is, then you have minus as well. Okay, so this is how you do the derivative. Then you put the derivative equal to 0. What was the meaning of putting derivative equal to 0? We did it in the last model, right? So took the derivative, put it slope is 0. When? Always? Capacity. Okay. Yeah? We are talking about capacity here. So he took the slope. First of all, he did multiply with the k. After that, they took the derivative and they are putting the derivative equal to 0. Okay. So this thing equals to 0. Okay. This thing equal to 0. Okay. So that means what? If I put this equals to 0, what will happen? You will take C on the other side. So what will you get? C log Kj over K equals to C, right? Okay. So what will happen? C. So this becomes what? 1. Clear? Okay. Now here it was K. Here it became K naught. What was K naught? 0, right? What was K naught? It was but what does it mean? Yes, K over 2, yes. Slope is 0. When? Capacity. But what is K? Density. So density, K naught is density when you have capacity. Clear? Yeah? Okay. It is K, by the way, it is K0 over 2 according to the previous one, not this one. Got it? Okay. So, why we are showing K naught? Because I put slope equals to 0. So this must be K naught, right? Because slope doesn't become equal to 0 at all densities. Okay? So that's why K is replaced by K naught. Clear or not? Okay. So this thing is equal to 1. Okay. So I can replace this thing with 1. Okay. I can replace this whole thing with 1. Okay. So when I replace this whole thing with 1, so this is equal to 1. So C equals to what? Speed. This whole thing became 1, right? So C equals to speed. Okay. But which is speed? No. U naught. Space means speed, yes. But which is space means speed? In what condition? Capacity. What? Clear or not? Any questions? Okay. So what were you doing? We had a Greenberg model. In Greenberg model, I have US, I know space means speed, right? I have K, I know density. Right? I have Kj, which was what? Jam density. I know that one. Okay. So I know these 3 things. But there is C here as well. So I need the value of C. So to get the value of C, I did all this thing. What? And I use the property of the capacity, and to reach capacity, slope becomes equal to 0. So once you do this, slope becomes to 0. That means everything is at capacity. Okay, so that's why we replace K with K naught and U with U naught. Got it? Clear? Okay. So C is the space means speed at capacity. Okay, so now we have 2 models, right? The Greenshield, the linear one, this one. Yes. Time? We finished? Why didn't you tell me earlier? Why are you wasting my time? Okay. So yes, let's start.